Welcome back. In the second part of this lecture, we're going to talk about actually doing some examples of finding extrema, and we're making it a little easy on ourselves. We're finding extrema just on closed intervals, and we're looking just for absolute extrema right now. So we're not really concerning ourselves as far as relative extrema yet. So if we have a closed interval, that's one of the things that allows us to use the extreme value theorem. So as long as f is also continuous on that interval, then we're guaranteed that we've got a maximum or a minimum somewhere. Now, we know that if you have an extreme value, a relative extremum, then that'll exist at a critical number. So that's kind of motivating the following. We'll start off by finding the critical numbers. And when we find our critical numbers, we're then going to figure out what is the y value for each of those critical numbers. So we're going to then say, okay, we found our critical numbers at here and here and here and here. We've gone back and we found out what our y values are. We know one of two things will happen. Guaranteed, we're going to have an absolute maximum and an absolute minimum because we have the side conditions for the extreme value theorem. We also know that if you have an absolute maximum, it'll either be one of the two endpoints or it'll be something that's also a relative maximum. So that means all we need to do is compare all the y values. The y values for all of our critical numbers, the y values at our endpoints. Whoever has the largest y value must be the absolute maximum. And then we'll do the same thing with all the y values, compare them and find out who's the smallest. And whoever is, out of the critical numbers for their y values and the endpoints, their y values, whoever that is, that will be the absolute minimum. And again, all of this hinges on that fact that if we're talking about an absolute maximum, it's either going to be something that's also a relative maximum. In other words, something like a hill that you happen to have in a graph. One of those points could be an absolute maximum. And same thing with relative minimums. They could potentially be an absolute minimum could potentially also be a relative minimum. Or you could have the absolute happening to be at one of the endpoints. So if we happen to have a graph that begins at an endpoint and stops at an endpoint and has some sort of shape in between that's nice and continuous, then either the minimum value will be at one of the endpoints or it'll be at one of the hills and valleys, at one of the critical numbers. So let's do some examples. The first one is this function, not a very nice function. It's a polynomial of degree 4. We're looking to find the absolute extrema on that interval from 1 to 5. So first things first, I know that f is a polynomial, and polynomials are continuous everywhere. So we are definitely continuous everywhere, which means we're also definitely continuous from 1 to 5. And so we're continuous on a closed interval, which means the extreme value theorem applies. That's important for us to think about because if the extreme value theorem did not apply, then there's no guarantee that one of the endpoints or one of the critical numbers would be a location for a maximum or a minimum. If you didn't have a continuous function or didn't have a closed interval, then maybe you don't actually have extreme values. But we're guaranteed that we will have extreme values, and we know it's going to be in one of a couple of places. So next move, I guess, is to find our critical numbers. And to find the critical numbers, we need to first find our derivative. So let's do that. Derivative of our polynomial 4x cubed minus 24x squared plus 32x. And critical numbers happen when f prime is either equal to 0 or f prime is undefined. This is definitely never undefined. It's a polynomial, so critical numbers will just happen when it's equal to 0. So let's do that. And I'm going to do a little bit of work here cleaning things up. I can factor x out of everybody, 4x out of everybody rather. And I can factor a little further. And I find three critical numbers. I found 0 and 2 and 4. Now, of course, we're only interested in the critical numbers that are inside the interval that we've been given. Our interval is from 1 to 5. So 2 and 4 definitely are in the interval, but this is not in the interval. So we are going to ignore 0. It's not going to be one that we're going to care about. We're not going to find the y value for it because it's outside of the 1 to 5 that we're actually interested in. So now, next thing we need to find out is what are all of our y values at 2, at 4, and also at our endpoints. So this is where we need to go back and use our original function to find out what is f of 2, and what is f of 4, what is f of our endpoints, 1 and also 5. So if you grab your calculator and grab the original function, so remember here, we're looking at the y values, that's the original function, not the derivative. And so when I put in my x value of 2 into the original function, I got a y value of 21, and at 4, I got a y value of 5. At 1, I got a y value of 14, and at 5, I got a y value of 30. So now we have the smallest y value of all happens to be 5, and that happens to be happening when x is equal to 4. So we can say that we have an absolute minimum of 5, and that happens at x equals 4. For the largest y value, I'm looking at this and it seems like 30 is the largest one, and that happens to be at an endpoint. So we can say that our absolute maximum happens at x is equal to 5. And the absolute minimum only happened once, and the absolute maximum only happened once. So there we go. We have an absolute minimum and an absolute maximum that we found. As far as relative minimums, in case you're wondering, or relative maximums, we're going to look at that in a future section. So this is not all that we could do with this one function. We might also ask ourselves, where are there relative minimums? Where are there relative maxima? Anyhow, we will leave that for the moment, and we'll continue on with another problem. All right, so we've got a little trigonometry problem here. I have a function 2 secant theta plus tangent theta, and it's on that closed interval. I know where secant and tangent are undefined. They both have vertical asymptotes at the same place, at pi over 2 and 3 pi over 2, all those odd pi over 2's. So that means those are places where g would be discontinuous. So g is discontinuous at positive and negative pi over 2, 3 pi over 2, and so on. And that's fine for us because none of those numbers happen to be inside that interval from negative pi over 4 to pi over 4. So that means that g is continuous on that interval. So that means the extreme value theorem applies. And we're guaranteed that we're going to have ourselves a maximum and a minimum because we have a continuous function over a closed interval. So first job, I guess, is for us to find critical numbers. And when I take my derivative of g of theta, derivative of secant is secant tangent. And derivative of tangent is secant squared. Critical numbers happen to be wherever g prime is undefined or equal to 0. And I know where g prime is undefined. And that's because it's also made out of secants and tangents, so it's undefined at the same place as g is, at pi over 2, 3 pi over 2, and so on. None of those are going to be included because none of those are inside of my interval, so I don't have to include them in my little table of y values when I start comparing for who's the largest, who's the smallest. So the only thing I now need to think about is, well, when is the derivative equal to 0? And so that's where our derivative of 2 secant tangent plus secant squared equals to 0. I could factor the secant out, giving me 2 tangent plus secant left behind. And now that I've done that, now that I have things factored and equal to 0, I can say that secant is equal to 0 and 2 tangent plus secant is equal to 0. For the first one, secant equals to 0, I know that there's no solutions, and that's because I know the graph of secant. I know that secant only has y values that are 1 and larger or -1 and smaller, so no solutions are going to come from that part of the equation. So hopefully we find some solutions from the second one, from 2 tangent plus secant equals 0. For that, it might be easier if I think about sine and tangent, as think about tangent and secant rather as sines and cosines. Tangent is sine over cosine and secant is 1 over cosine. So if I'm looking at that, I could really make it a lot easier for myself by multiplying both sides of the equation by cosine. That would give me 2 sine theta plus 1 equals to 0. I do have to make a little caution to myself, though, since I'm multiplying by something involving a variable, potentially I could be introducing extraneous solutions. If I did, those would happen when cosine is equal to 0, which would be at pi over 2, 3 pi over 2, and so on. Conveniently enough, none of those numbers are included in my interval, so I don't have to worry about any extraneous solutions that might come up. And in fact, no extraneous solutions come up because when we solve this, we look for where is sine equal to -1/2, and we find that that's at -pi over 6. So it looks like we're only going to have 3 things to look at. We'll have -pi over 4 and +pi over 4. Those are our 2 endpoints. And then we'll also have -pi over 6. Okay, so for pi over 4, putting that into our original function, 2 secant plus tangent. Secant of -pi over 4 is root of 2, so we'll have 2 root of 2. And then tangent of -pi over 4 is -1. And that's about 1.828 thereabouts. G of pi over 4, putting in pi over 4 in for secant, that's root 2 again. And putting pi over 4 in for tangent, that's +1. So 2 root 2 plus 1, that would give me 3.8 thereabouts. And then finally at -pi over 6, secant of -pi over 6 is 2 over root 3. And tangent of pi over -pi over 6 is -1 over root 3. So that gives me 4 over root 3 minus 1 over root 3, 3 over root 3, which is the same thing as root 3. And as a decimal number, that's about 1.73-ish. So now I can see that I definitely have my maximum and minimum in sight. I can say that the maximum value is, of course, the largest of the 3 y values, and that is 2 root 2 plus 1, and that happens at x being pi over 4. And then the minimum value, that happens to be one of our at one of our critical numbers. The minimum value is square root of 3, and that happened to be at -pi over 6. All right, one last example. We've got this rational function, and I want to find the absolute extrema on the interval from -2 to 1. So I know that there's only one place where f is discontinuous, and that happens to be at x equals 2, which is not included inside of our interval. So f is definitely continuous on that interval. And since it's continuous on an on a closed interval, then that means the extreme value theorem applies. So we're guaranteed we're going to have a maximum and we're going to have a minimum. So let's go ahead and start finding our derivative and see what that does for us. Because of course our next move is to find all of our critical numbers. I'm starting off here doing my quotient rule since f is a quotient. So bottom was squared, bottom came up, derivative of the top minus the top as it is, and then times derivative of the bottom. And if I were to clean that up a little bit, I would have x times 2x. I'd have 2x squared minus an x squared, which is 1x squared. I'd have minus 4x, and I would have plus 1. And this is all over x minus 2 whole thing squared. So when we're looking for critical numbers, they are where our derivative is either undefined or equal to 0. And so f prime is undefined at x equals 2, and that's not a surprise because f is undefined at x equals 2. But 2 is not part of our interval, so we don't need to care about it. It won't be included in our little table of values later on. The other critical numbers that we'd be interested in are where f prime is equal to 0. And for that, since it's a fraction equal to 0, we know that that only happens when the numerator is equal to 0. So really, what we'd be solving is solving x squared minus 4x plus 1 equals to 0. That doesn't factor very nicely or at all, so instead I would say use the quadratic formula. And when I use the quadratic formula for this, so when x is negative b plus minus root of b squared minus 4ac all over 2a, and clean it up. So after I run that through and clean it up, I get to x is 2 plus or minus root of 3. And of course, I want to check to see which of those numbers happen to be inside my interval. Maybe both are, maybe neither is. So on the side, I'll do a little quick calculation, and I find that 2 plus root 3 is a little bit too big. 2 plus root of 3 is about 3.7, which is too large. Our interval only goes up to 1, so we're not going to include 2 plus root 3. And 2 minus root 3, I calculate that out. That's about 0.2679. That's definitely inside my interval, so that will be one that I'm going to include. Okay, so I have found 3 critical numbers, 2 of which I'm going to ignore, x equals 2 and x equals 2 plus root 3, because neither of those are inside my interval. So really, I only need to look at the endpoints of my interval and also 2 minus root 3. So I guess that's my next job, is to figure out what's going on at my endpoints. So at -2 and at +1. And then I also need to figure out what's happening at my critical number, the one that's actually inside my interval. For putting in -2 into my function, that'll give me 3 for the numerator and -4 for the denominator. So -0.75 is my value for the y value when x is -2. And when x is equal to 1, we have 0 in the numerator and -1 in the denominator. So 0 is my y value. And for 2 minus root 3, so let's put that into our function, we get 2 minus root 3 squared minus 1 all over 2 minus root 3 minus 2. So the denominator clearly cleans up nicely. I've got a minus root 3. And in the top, if I were to expand everything, I would have 4 minus 4 root 3 plus 3, and then minus 1. So that's 6 minus 4 root 3 over root 3. And if you were to clean this up a little bit further, I could go one step further and say, well, really this is, I'll drop my negative there, it is 6 over negative root 3 and minus 4 root 3 over negative root 3, which when we clean that up, of course, the negatives will cancel and the root 3's will cancel, leaving me plus 4. And 6 divided by negative root 3, that's the same thing as negative 2 root 3. So if I run that through my calculator, I have 4 minus 2 root 3, and what does that turn out to be? 4 minus 2 root 3 is about 0.5-ish, about 0.536, thereabouts. So now looking at my y values that I found, negative 0.75, 0, positive 0.536, I can definitely say that we have a maximum, the maximum value, and that happens to be the 4 minus 2 root 3, and that happened at the x value of 2 minus root 3. That's our largest y value, was that 0.536-ish. And then our smallest y value happens to be the negative 0.75. So the minimum value is negative 3/4, and that happens to be at x is equal to negative 2.